Good morning, everyone. My name is Ray Wells, and I'm a research chemist at the National Institute for Occupational Safety and Health, or NIOSH, in Morgantown, West Virginia. And I'm very interested in the indoor environment and the chemistry that occurs there because of the association between, as Paula mentioned earlier, the indoor environment and health effects. And in order to understand that, we have a program at NIOSH called the Health Hazard Evaluation Program, where workers can call in and request assessments of their workplaces to try to find issues or try to understand their work environment. And in the last 5 years, 36% of those HHE requests have dealt with the indoor environment quality. So this is as Paula mentioned, this is an important issue that we're very interested in and trying to understand. So for us, being able to understand or describe the chemical composition of the indoor environment is important for describing the risks to the occupants, explaining the observed health effects, and then also assessing the effectiveness of implemented controls or technologies. We've got three very good speakers to start off our day. Rich Corsi, from a dean at Portland State University, but before that he was at UT Austin, where he built a large research group on looking at indoor chemistry and the indoor environment. I'm going to steal a quote from Dustin Poppendick. Rich's passion for indoor quality was shared. He'll share even by passing to a passing squirrel the importance of the indoor environment. That was one I had. Alan Goldstein is a professor at UC Berkeley, and like Paula, he's also a AAAS fellow. His experience in atmospheric chemistry and method development is well known and has been brought in to help us understand the indoor environment in much greater detail. Nina Vance is at the University of Colorado Boulder, and she's been there since 2016, and she'll talk today about some outcomes from the important home chem project. And this is, she'll give you a lot greater detail, but over 60 scientists completely outfitted a home in Texas, the test home, to look at all of the different impacts. And I think Nina's the only person to have 3 Thanksgivings in a month, so that was good. So anyway, I would like to introduce Rich Corsi.
Well, thank you to Ray, and thank you to Dustin, I think, for that quote about squirrels. Thank you to AAAS for organizing and hosting this really important symposium today, and thank you to Paula and the Sloan Foundation, as always, for supporting this important field. So I'm going to prime the pump, I hope, for the rest of the speakers today, and try to do so by answering 7 questions. 7 basic questions about indoor chemistry. Why do we care? What's our motivation? Where does it occur? What are some important sources of reactive pollutants indoors? Why are surfaces important? Are environmental conditions important? Why are building occupants important? And where do we go from here? And so I have to answer those 7 questions in the next 15.5 minutes. And so I ask all of you right now to please fasten your seatbelts. It's going to be a fun ride. So why care? Many of you have seen this before, some of you haven't. This is the secret code for those of us who do indoor air quality research. All of these have the same units, they're years. 79 years is the average life expectancy of an American. The average American will spend 69 of those 79 years, actually slightly more than 69 of those 79 years, domiciled inside buildings. We're indoor creatures. We spend a greater fraction of our lives inside of buildings than whales spend submerged below the surface of the ocean. Think about that. 54 is the total number of years that we will spend inside of our residence, in our home during our lifetime. So our homes are incredibly important environments when it comes to exposure to stuff in air and surfaces. 26 is the total number of years you'll lie horizontally on a mattress with your mouth pushed up against a pillow that's emitting toluene diisocyanate from the polyurethane foam inside. 6 is the total number of years that you'll spend outdoors during your lifetime. 4 is the total number of years you'll spend in a motor vehicle. So by virtue of the fact that we spend so much time indoors, you can imagine that the indoor environment will affect our health, will affect our productivity, will affect our ability to learn. The equation that I've shown here is basically a way of articulating our total mass inhaled of pollution in the indoor environment divided by the total mass of air pollution we inhale in the outdoor environment, all right? So we take the concentration, mass per unit volume indoors, the time spent indoors, the breathing rate indoors, and the same outdoors in the denominator. And then I've just sort of put that in terms of ratios of each of the important terms here. Gone to the literature, found numbers for, we already know how much time we spend indoors, but breathing rates indoors and outdoors, and levels of a wide spectrum of pollutants indoors and outdoors. And what you find when you plug into this very simple equation is that for pollutants of outdoor origin, those that originate outdoors, the ratio of the mass inhaled inside buildings to outdoors is 1 to 10, right? Even for pollutants of outdoor origin, we inhale most of those pollutants indoors. And for pollutants that are primarily of indoor origin, where we see higher levels of those pollutants indoors than outdoors, the ratio ranges from about 25 to 100, depending upon the specific pollutant. So no matter how you cut this, our exposure to air pollution is dominated by air we inhale indoors. You'll hear today that chemistry has a significant influence on pollutants inhaled indoors. And as a building scientist, that excites the heck out of me because that means we have great opportunities to reduce population exposure to air pollution by the way we design and operate our buildings. And perhaps even looking to the future, as Paula just alluded to, perhaps in the future we can actually even optimize chemistry inside of buildings to make the building environment even healthier. So one question down. Number 2. Where does chemistry occur in buildings? And there's lots of different types of chemistry that happens in buildings. But the answer is everywhere, right? So chemistry happens in the air and the gas phase, in the occupied space of buildings. It also happens in unoccupied spaces. It happens in attics. It happens in crawl spaces. It happens in wall cavities. It happens in mechanical systems, HVAC systems. It happens on surfaces and inside materials as well, building materials, furnishings, on us, our hair, our skin, our clothing, and also in unoccupied spaces where materials tend to be a lot different than in the occupied space. It happens in the aqueous phase and in water films that build up on surfaces. It happens in plumbing, premise plumbing. It happens in dishwashers and washing machines. And it happens on airborne particles, in airborne particles, and also those particles that deposit on surfaces. It happens everywhere, right? And some of these really need a lot more exploration. Number 3, what are some important reactive sources in the indoor environment? Certainly outdoor environment contributes ozone to the indoor environment, contributes oxides of nitrogen, unsaturated hydrocarbons. And then in the inside of buildings, we have a lot of primary sources that emit unsaturated VOCs, SVOCs, NOx from combustion sources, lots of unsaturated VOCs from fragrances and air fresheners, and so on and so forth. I list chemistry here because chemistry is also a source of reactive pollutants. Chemistry generates more reactive pollutants, and you're going to hear about that today. But there are lots of sources of reactive pollutants in the indoor environment. In terms of ozone, we know that ozone is continuously coming in from outdoors, day and night, every hour of the day, sometimes more, sometimes less. And so that's the major source of ozone in buildings. But there are also some indoor sources, and I list some of these here, from ion generators to electrostatic precipitators used in mechanical systems, which can be highly effective at removing fine particles from indoor air, but at the same time can generate large amounts of ozone, sometimes a lot more ozone than would come in even from the outdoor environment on a smoggy day, right? The right side here, you see a plot that tries to articulate the importance of even small amounts of ozone generated by an ion generator in the indoor environment. And what you see on this plot is the equivalent outdoor ozone concentration increase, how much we would have to increase outdoor ozone concentrations to give us the same amount of ozone indoors as is generated by an ion generator, emitting, if the green line, 5 milligrams per hour of ozone. And you can see as you change the air exchange rate in a median-sized US home, and you get down to about 0.25 air changes per hour, which is actually not that unrealistic anymore. you're talking about a 40 to 50 part per billion equivalent increase in outdoor ozone concentration. That's a lot, all right? So just putting one small ion generator that emits some ozone in a home can actually contribute a lot of ozone to the indoor environment. So ozone will react with other reactive sources in the indoor environment. So there's been a lot of research done on ozone reactions with terpenes and terpene alcohols that come from green cleaning solutions, fragrances, air fresheners, personal care products. And when ozone reacts with these terpenes and terpene alcohols, you get a whole lot of stuff formed, including low vapor pressure compounds, those little red dots up there. And these low vapor pressure compounds can self-nucleate, they can form particles when they come together, or they can attach to, they can condense on, they can absorb into, they can adsorb to existing particles in the air and grow that particle mass. We call this secondary organic aerosols, SOA, right? So what I've shown in this plot here is a simple example from an experiment we did in a chamber at the University of Texas, about the size of a small residential bathroom, about 11 or 12 cubic meters. And we held the ozone concentration in that chamber. It's somewhere between 30 and 50 ppb. It's been a while now. But, a reasonable ozone concentration. And we looked at what happened when we then placed a solid air freshener inside the chamber. One solid air freshener that emits a mixture of terpenes and terpene alcohols. The vertical axis is the number of particles per cubic centimeter. The horizontal axis is time. And you can see at time equal to 0, between minus 50 and 50, when we put the solid air freshener in the room, we get an increase in the nanoparticles, the 0.02 to 0.1 micron range, from about 6,000 per cubic centimeter up to 700, 800,000 per cubic centimeter, really quickly. That's how fast the chemistry is between ozone and these terpene mixtures. I'm not going to go into the rest of what's on this plot, but you can ask me about it later if you're interested in the growth wave. But if we have this kind of chemistry going on, you're also forming lots of other types of oxidized products that you're going to hear about today. Ozone will also react with stuff from combustion sources, especially nitric oxide. So in this plot, which happened to be an experiment done in a professor's house at the University of Texas, the professor's at the podium right now, and you can see an ozone concentration sort of midday here of around 25 parts per billion in the living room of this house. And right after 1300, right after 3 p.m., 2 gas burners were turned on a stove in the kitchen adjacent to the living room. Watch what happens to the ozone. It's essentially titrated, and it's titrated really quickly when ozone reacts with nitric oxide, which is one of the fastest reactions that happens in air inside homes. The bimolecular reaction rate constant for this reaction is very high. If you assume a steady concentration of 50 parts per billion of nitric oxide, you get essentially a removal rate for ozone or for nitric oxide of 80 per hour. Compare that with a typical air exchange rate in my old home in Austin, which I would measure regularly, about 0.3 to 0.4 per hour. So this is a very fast reaction, very fast removal of ozone. So this is chemistry that happens every day in people's homes, both of the examples that I just showed you. Number 4, why are surfaces important? Well, as Paul alluded to, there's surfaces all around us indoors. The surface area of all the materials in most buildings normalized by the volume of air in the building, the surface to volume ratio, is typically between 300 and 1,000 times what it is outdoors. So pollutants have a lot more surfaces to interact with indoors than they have outdoors, and those pollutant interactions are important. There are dramatic differences between surfaces and materials indoors. The carpet in this room is much different than the skin oils on your face, thank goodness. And these materials are dynamic, they age with time, they accumulate organic matter, particles deposit on them, they change with time, they're emission sources, and there's significant interactions with pollutants. Gases stick to materials, they can stay there for different amounts of times before they desorb. Particles deposit on surfaces, you know that when you clean the dust in your house. Those dust particles or any kind of particles can be transformed by the surfaces and then resuspended, and we breathe those transformed particles. And chemical reactions can also occur. So I'm going to give you some examples of these right now. This one happens to be my team did a lot of research on individual chemicals, mixtures of chemicals interacting with lots of different materials. This is just one example of dichlorobenzene, orthodichlorobenzene, reacting with, or sticking to, adsorbing to carpet. And the way to look at the plot on the right is that the vertical axis corresponds to the concentration or the amount of pollutant inside of a stainless steel chamber. What we do is we put these materials in a stainless steel chamber, and we pass high purity air over the materials, and then we start injecting a chemical in, and we look at how much is taken up by the material over time. So the vertical axis is the concentration in the chamber normalized by the concentration that we're injecting into the chamber. and the horizontal axis is time, right? So you can see several curves on here. The important point is that that solid line at the very top is the no-stick line. If there's nothing adsorbing to the material in the chamber, we should be sitting on that no-stick line at the top. The closer we are to that no-stick line, the less adsorption we have. Right here you have the carpet system. So this is the carpet in its full glory with an underlying polyurethane foam cushion, backing, and fibers. And you can see a significant amount of removal. That's pretty far away from the no-stick line for dichlorobenzene to carpet. Right here, the pink squares, you have the nylon fibers. Nylon fibers, almost no dichlorobenzene sticks to the nylon fibers, right? The green triangles are the polypropylene backing that hold the fibers in place, so there's some adsorption to the polypropylene backing. And these dashed blue lines are the bonded urethane cushion, all right, the polyurethane foam underneath the carpet, if it's just sitting there by itself with nothing on top of it, not as a system. The moral of this story is that polyurethane foam is a huge sink for lots of different chemicals in indoor environments. If I was to take a sample of anything in this room to tell you what's been in this room in the past, I would take a sample of polyurethane foam on the seats that you're sitting on right now, all right? Tends to be a reservoir of chemicals that have been in an environment over periods of time. Particles also deposit on surfaces and can be transformed on surfaces. So imagine dust on a bookshelf or on a countertop in your home or on the floor, right? When those dust particles or any kind of particles deposit on a surface, they sit in a small boundary layer, the thickness of the skin of an apple, all right, on that surface. And that boundary layer can be quite concentrated in terms of the level of pollutants that are coming out of the material, say a plasticizer, phthalates, or flame retardants that are leaching out of the material very slowly, right? So now we're immersing these particles in this boundary layer of relatively high concentration of these chemicals, and the particles can become contaminated, especially the organic portion of the particles. If we then resuspend those particles when we walk on it or our infant crawls on the floor, right, or wherever it is, right, those particles that are contaminated can become a vehicle for the transport of flame retardants and plasticizers and other things into our lungs. So one of my colleagues at the University of Texas did some research in our test house at the University of Texas, a 3-bedroom, 2-bath test house. And what she noticed was that the flooring had lots of butyl-benzyl phthalate in it, a plasticizer. None of the other materials in the house had butyl-benzyl phthalate on it. So she hypothesized that if she collected dust samples from the flooring, the dust samples in the flooring should have lots of butyl-benzyl phthalate in it, and from other surfaces you'd see less of it. And here's the result, all right? Butyl-benzyl phthalate concentration in micrograms per gram. We're up in the milligram per gram level here for dust samples collected off the floor, which is the red bars, and then off of all the other surfaces, you see the green bars, very little butyl-benzyl phthalate in it. So the surfaces, the materials that particles actually land on can transform the particles, and that affects what we're actually exposed to when those particles become resuspended. We also know that pollutants chemically react with materials. So ozone is the one we know the most about. There's been a lot of research on ozone. Ozone will react with reaction sites on materials, and sometimes those reactions lead to the production of what are called ozone reaction products or reaction products, which can be released from the material, sometimes almost instantaneously and sometimes hours to days later released from the material. And the plot that I show here is a plot that shows deposition velocity. Don't worry about what that means. It's just a measure of sort of how reactive a material is, all right? In this particular case, the fluid mechanics are the same for every material, so the differences that you see are actually due to reactivity. These are for about 10 different green building materials from some research we did about 10 years ago. And the important points here is that if you look at how that reactivity changes with time of exposure to ozone, you see a significant difference in the reactivities between materials. Not all materials are created equal, like has already been said. You see declining reactivity in every single case. As the reaction sites are wiped out on a material, it becomes less active for removing ozone. You see, interestingly, for some of these materials, a non-zero floor. It basically converges to a steady removal rate of ozone. We have reasons why we think that might be happening, but we're not sure. The question is why. And then also when we turn the ozone off and then turn it back on 24 hours, many of these materials regenerate. They go back to their original reactivity, even though they're sealed off in a chamber with no airflow over them. Why, right? So these are questions, we've kind of scratched the surface on many things in the past in this field, and we haven't had the resources to dig deeper and answer some of these questions. And I think this is a really good example of that. I think with more resources and more people coming into this field that have heavy weapons in terms of instrumentation, maybe we'll start to answer some of these questions. Are environmental conditions important? The answer is yes. We typically measure temperature in the air and relative humidity in the air. That's not everything we should be measuring. We should be measuring things like surface temperature indoors and some metrics for mixing conditions in the indoor environment. I show a couple of plots here just for temperature effects. The top plot shows reaction rate constants for ozone and alpha pinene, normalized by the reaction rate constant at 25 degrees C. And what you can see here is you vary over temperatures. You don't see a very big effect of, especially within the temperature range of buildings, you don't see a big effect on reaction rates in the air. So temperature in buildings doesn't really affect reaction rates in the air. It can have a big effect on secondary organic aerosol formation. So the equilibrium state tends to stay towards the solid phase or the particle phase when you lower temperatures. So even within reasonable temperatures, say 17 to 27 degrees Celsius in an indoor environment, you do get a factor of 3 or so change in secondary organic aerosol formation as you move to cooler temperatures. So in that particular case, temperature of the air does make a difference. And environmental conditions also matter on surfaces. In the left plot here, I show the temperature of the surface of a plastic laminated table put next to a table, and the table is placed next to windows of different efficiency, all right? So we're just going to look at one of those, and that's the least energy efficient, which is the black curve. And what you can see on this black curve as you progress through a day, the temperature of the surface of this table goes from about 24 degrees Celsius to above 34 degrees Celsius. Over a 10 degrees Celsius change in the temperature of the surface over the course of the day. Why is that important? Well, that's particularly important if we're emitting semi-vol organic compounds, if we're emitting plasticizers from that surface. A 10 degrees Celsius change in the temperature of many indoor materials that have plasticizers in it can be an order of magnitude increase in emissions, a factor of 10 increase in emissions. So surface temperatures are important, especially when it comes to things like semi-VOC emissions from flame retardants and plasticizers. On the right, okay, Ray? Good, okay, on the right is a result from some field experiments that we did in homes in Austin, Texas. I wanted to show you the effects of relative humidity or changes in relative humidity on organic compounds in air. We'd go into homes, we'd turn on a humidifier. I know Barbara's going to talk about water-soluble organic compounds in a little bit. We turn on a humidifier, we increase the humidity from in reasonable bounds, 40 to 60%, 45 to 65%. We measure the total amount of organic matter in the air before humidifying and after humidifying. Before humidifying is the blue bars, after humidifying is the red bars in this plot. This is abundance per volume of total stuff in the air. We also did mass spec analysis to identify what the red bar was made of, all right? And what we found in the red bars was not chemicals that would be associated with materials in the indoor space, but chemicals that would be associated with having adsorbed to materials. These are fragrances. These are terpenes and terpene alcohols, paradichlorobenzene used in moth repellents, those kinds of things, right? So this is fascinating to me. What does this mean about damp buildings and damp spaces? If things get damp, do we get gushes of chemicals emitted into the air in buildings? If we change our thermostat setting to conserve energy, do we have periods of higher relative humidity indoors? Does that expose us to more chemicals? An area of research need, big research need here, understanding the mechanisms and understanding how we might optimize these effects to purge buildings from things that are stuck to surfaces. Why are building occupants important? Our activities, right? We bring sources into the indoor environment. We plug in air fresheners. We change thermostats. We cook. We modify surfaces by vacuuming and dusting. We influence ventilation by opening windows and so on and forth. But we're also reactive ourselves. Our skin lipids, things like squalene and skin lipids, it's highly unsaturated, is reactive with ozone. Our clothing, personal hygiene products, et cetera. And the plot on the right just shows an experiment from Denmark, from Charlie Wester and Armin Visthaler, that showed two large Danish men, quote, large Danish men, walking into a chamber that was held at 33 parts per billion ozone. At 10 a.m. they walk in, you see a drop in ozone concentration. At the same time, you see a burst and increase in 6-MHO and 4-oxopentanal, which are reaction products with squalene. All right. So where do we go from here? I think I'm out of time, is that right? I am out of time. So I'll just let you look at this. I just want to point out the first one. There's been a lot published on this subject where we've scratched the surface and found some interesting things. I hope those of you that are just getting in the field read the literature. There's a lot of publications, especially on ozone chemistry indoors. Please read the literature, and you'll have access to that slide, I think. Let's have a great day. These are some of my past research sponsors on the lower right. Follow me on Twitter, please, especially since that's videotaped live here. Follow me on Twitter, everybody. And you can also email me if you have any questions.